this whole unit together in less than, I don't know, 8 minutes. We'll see how it's possible. So we finished working with all kinds of polynomials, and if you remember, one of the simplest polynomials was a straight line, right? Y equals mx plus b, linear equation. We can change the slope, which changes the steepness, and we can change the b, which changes the intercept, right? The starting point down here. We can do that. All right, and we're going to talk about in this unit, we're going to review just a little bit of linear sequences. So in terms of a line has all data points, right? So I can enter any, just do a table here. Insert a table, right? So a linear function can have any value of x. So if I was using this equation, let's even get rid of let's make it be something, let's say 5x plus 10, right? So we have an exact line here. So when x is 0, y is 10, right? We got a dot here. And the line has every value in between. So even when x is of some, let's say a fifth, right? X can be 1/5. 1/5 times 5 is 1, plus 10 is 11, right? And I get the next point, and I have all these points, and I couldn't possibly graph them all, right? Because they're everything in between. We're going to talk a little bit in this unit about sequences, and we're going to talk about geometric and arithmetic sequences. Arithmetic sequences are just lines, but instead of having all values, we can only have whole numbers. So we could have 1, when x is 1, it's 15. We just get these points. So when x is 2, we're going to have 20, right? Only the whole numbers, because in a sequence, we're talking about these values, 10, 15, 20. And we're really just talking about situations where only whole numbers work. And in real life, this is very common, right? Because we can't often buy parts of something. So if I'm at the store, or let's say my cell phone is going to be $10 to start, and then it's going to be 5, let's say 5 per, I don't know, 3 gigabytes. I don't know how it's measured. But the point being that we have to pay for these whole number things, right? So we're going to quickly review linear functions with arithmetic sequences. And then we're going to add on to this exponential functions. And in exponential functions, we have some base. So we could again use 5 here, but we're going to have it be some value that it's being multiplied. And we have to remember with our exponents that first we first do exponents, and then we multiply it times 5. And we see here that in the very short term, right, very down here, very early on, I could get these to maybe be even closer, right? 1.5, nope, not so good. Let's say 5. At the very beginning, I can get exponential and linear to be fairly close. If I zoomed out, it would even look closer. But as time goes on, exponential does this like super growth, and linear stays at a constant rate. So we're going to look at how the rate of change for linear stays constant, and for exponential growth, we're going to have a rate of change that gets faster, 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 faster. And we're also going to see that if we wanted to, we could go the other direction. This is called decay, exponential decay. And when we're talking about exponential growth and decay, we can talk about a geometric sequence. And again, the geometric sequence is going to be just like an exponential function, but instead of having all values, we're only going to have whole number values. All right, so those are two big ideas. The other one is going to be, how do I end up solving this? Like, let's say I want y to be 100. Oh, too big. Y to be 80. How do I find this value, right? So I end up, see if I can type here, I end up having 80 equals 5 times 3 raised to the x, right? And I ended up with that same value because this is just an equation. But how do I find x, right? We've always done inverse operations, but what's the inverse of an exponential function? And we're going to see the inverse of an exponential function is something called a log function. So the first half of this unit is going to be working with these linear functions, geometric sequences, and kind of setting up all the different word problems that apply to exponential growth or decay. And then we're going to figure out how do we solve them. And we're going to need log functions. So how did I do? I can't see how much time, but I think I was under 8 minutes, and that's what we're going to learn in this unit.